Hi, welcome back. In this lecture, I'm going to discuss MPI one-sided communication. Until now, we have been discussing MPI two-sided communication. In the MPI two-sided communication, we always have two processes involved in the communication. We have the MPI send, that is sending the message, and for each MPI send, we need a matching MPI receive. So that's why in MPI two-sided communication, always two processes are involved in the communication. In the MPI one-sided communication, we have only one process that is actively participating in the communication. That's why it's called MPI one-sided. So most of the material is based on the Supercomputing 14 tutorial presented by Pavan Balaji, William Grob, Torsten Hoffler, and Rajiv Thakur. And as usual, most of these slides also have been adapted by from the Bill Grob's teaching material at the UIUC. So what's the basic idea of one-sided communication? Well, the basic idea is of one-sided communication model is to decouple data movement with the synchronization. In a MPI two-sided, we see that each message receive introduce a basic synchronization mechanism. Here explicitly we need to synchronize the communication. One-sided communications should be able to move data without requiring the data movement process to synchronize. So we are removing a synchronization step at the remote process that the two-sided communication model requires. So how is it working? Well, the way it's working is very similar to the biggest languages. So we have one MPI process exposing part of its own private memory to all the other processes. So each process exposes a part of its memory to other processes. So once this memory is exposed, each process can directly read from or write to this memory, right? So the first step is to expose the memory, and then we do read operation or write operation. The read operation in MPI one-sided communication is also called get. So whenever I use the say MPI get, it will be read from MPI window, while the writing operation to a remote MPI window is called put. Right. So I will use MPI put to write to a remote memory window. So what are the basic eventually of using one-sided instead of two-sided programming? Well, so these diagrams give an idea. So in the top panel we have the MPI two-sided. So we have a send, and also because it's two-sided, we have a matching receive on the process that is receiving. Because of the receiving message need to post a receive to make available a buffer to communication, this availability of the buffer at the receive side might be delayed if the process is on delayed. On the contrary, with the MPI one-sided communication, we start writing to the MPI window. This memory has been accessible by all the processes, and then we can just return. So we don't need a matching receiving that that might be delayed by some delay that is occurring on the processors. So we can actually write to using put, but also we need to get data. Then we might want to synchronize explicitly in order to ensure that our data is on process 0 or on process 1. What are the advantages of RMA operation, so remote Windows operation? Well, one of the advantages is that we can do multiple data transfers with a single synchronization operation. So we can keep inputting and get operation, and then when we want to ensure that the data is actually there, we need to synchronize, right? And we can use just one single synchronization operation per multiple data movement operation. We will see that also the MPI one-sided doesn't use tags. So these we can bypass tag matching. The receiving side, we also need to check if the tag is the same one that has been sent in the two-sided communication. In the one-sided communication, we don't need to do that. So we remove a part of the head due to the fact of tag matching. Some irregular communication patterns, for instance, all the communication patterns that are in graph application can be efficiently expressed by using MPI one-sided communication. So when, for instance, we have distributed graph and we want to just put some values in some part of the graph that is not on the process, we don't need to. It's quite clumsy to use MPI send and receive. Instead, here we can just expose the part of the graph to all the remote processes, and then we can do put or get operation to update the values of a particular node of the graph. In many systems, MPI one-sided also can be faster than send and receive if there is hardware support for remote memory access, such as a shared memory system. I told you that one advantage is actually to express communication pattern in for instance, in graphs. So if communication pattern is not known a priori, but the data location are known, so for instance, like a distributed graph, the send receive model requires an extra step to determine how many sends received to issues. However, RMA can handle this quite easily because only the origin or the target process need to issue the put or the get call. This makes dynamic communication much easier to program. So what we need to know about MPI RMA? Well, how do we create remote accessible memory? And in particular, we need to know how to read, write, and update in remote memory. We need to understand data synchronization and understand the memory model. So the first step is actually to look at how we can create this part of the memory that can be exposed to all the other MPI processes. That means that we want to create an MPI Windows. So how this works? Well, so by default we can use a malloc or the new operator in C and C++ to create a memory within like a variable or an array that is local to the MPI process, right? So by default, only all the mallocs and new created within the process are only accessible by that MPI process. So for instance, in this case, we alloc and for instance an array that is x, and the size is 100, and this x will be only accessible by that MPI process. So once the memory is created, the user has to make an explicit MPI call to declare that memory region as remotely accessible. So let's say I want to make accessible this X to all the other processes. So I want to be able that other processes can update directly this X variable. So the MPI terminology for a remotely accessible memory is a window, right? So we will say that an MPI window is a memory on a process that is accessible by all the other processes in the communicator. There is a slightly distinction between window and a window object. So a group of processes collective create a window object, right? So we talk about a window object when a group of processes creates this window. The single memory that is acceptable by all the other processes within one MPI process is called MPI window. That is, in MPI terminology, different by window object. So once a memory region is declared as remotely accessible, that means that we create our MPI window. All the processes in the window object can read and write data to this memory without explicitly synchronize with the target of the process. So let's see here an example. We have for processes, right? And each of these processes is exposing to all the other processes a part of his own local memory, and he do that by allocating, by exposing part of this memory using the MPI window. So the gray part here is the part of the memory that is being made accessible by all the other processes, right? So the yellow part is the memory space within one process, and then we can decide to expose the limited part of that memory space to all the other processes. So this one window, right? So then once this is acceptable, we can use the put operation to write. So for instance, in this case, the process 0 is writing directly to this MPI window that has been made accessible by process 3, right? We can also do get operation that is basically a read operation. So what are the basic RMA function for communication? Well, the first function that we are going to look in this lecture are basically how to create these MPI windows. We see that there are like 4 different types of creating. The most used one are the first 2, but there are MPI Windows function to create the MPI windows. So we look at MPI Win create and MPI Win allocate that expose local memory to RMA operation by other processes in the communicator. So this is collective operation, so all the processes need to be involved, and this creates also a window object. We also then need to remember that to allocate these MPI windows, we're using MPI Win free. So then we have data movement and aggregation operation. So we have the read and the write operation. So the write is MPI put, the read is the MPI get, and then we have a function for accumulating data to Windows, like MPI accumulate updates to update remote memory using local values. And also very important, we will discuss synchronization operation on MPI window object needed to ensure that the operations are actually complete. So let's start on looking at different ways to create MPI windows. In MPI, 4 models exist. We will focus on the first 2. The first one is to use MPI Win allocate to allocate first MPI within MPI process, and then we use MPI Win create. Right. So this works if MPI Win create is only works that if we have been allocated buffer that we would like to make a remotely accessible. So we will create this buffer using MPI Win allocate, MPI allocate. The second one that is basically combining the MPI allocate and the MPI Win create in just one function is called MPI Win allocate, right? So in this case, we want to create a buffer and make it directly accessible by the remote process. And then there are other two window creation model. So one is MPI Win create dynamic. So that means that we don't have the buffer yet, but we will have one in the future. Also, we will have MPI Win allocate share. So if we want to multiple processes on the same node to share a buffer, right? So this can, for instance, be used for a shared memory program instead of OpenMP. So let's look at MPI Win create function. So the MPI Win create function is expose a region of memory in RMA window. So one of the argument is basically the name, the pointer to the a handle to the window object, and then we provided the following arguments. So we have the base pointer to the local data to expose. So we allocate some memory, and then we basically provide the the base pointer to local data. We provide the size of the local data in bytes, and then we provided what is the displacement units in the window. So that is the local unit size for displacements in bytes. And then we provide an info object that is typically used for optimization or to give some information about the hardware, and then to handle the communicator and the window. So let's see how this works with a simple example. So this is, as I told you, MPIWinCreate requires to allocate first memory. So in this case, we are calling MPI allocate memory, and we create an array A of integer, and then we create MPIWinCreate using this buffer, and then we give the size, and then we give the displacement units in this case. So these are, remember, this is in byte, so it's the size of integer. And then at the end, we always need to remember to free the memory that we have been allocated. So MPIWinAllocate is another function that is basically combine the MPI allocate with the MPI create. So it allows us to create in just one shot MPI windows. So MPI window allocate create a remotely accessible memory region in an RMA window. So only data exposed in a window can be accessed by RMA operation. So the arguments are similar to the one MPIWinCreate, but in different order. So we need to provide the size of local data in bytes. We need to provide still the displacement unit, that is local unit size for displacement in bytes. And then we provide the info object handle to the info object, handle to communicator, and handle to the windows, and also need to provide the pointer to expose the local data. So let's see how this looks like. So you see that the code is much shortened because we don't need to create our buffer before. So in this case, it's just one call, MPIWindow allocate the size, the displacement units. There is no info object handle, so we provide MPI info null handle, communicator, and our window handle to the window object, and basically the pointer to our A. So at this point, A is now accessible for all the processes in the MPI core world, and also we need to remember to free. So this is the last slides. Next lecture, we're going to look at data movement operation in MPI one-sided, and start looking at synchronization operation. Talk to you soon.